Hey, Micah, feel free to ask me questions if you have any while we're waiting. We're quite a bit early. I'm just copying some notes down and stuff. Still got one more minute left. Anybody have any questions? Again, feel free to ask. I noticed y'all went ahead and typed your names in the chat. Thank you for that. So we've already got your attendance going. Right, it's just about time. I don't really have that many people, but I'm going to give it a little bit more time just to be sure. All right, I guess we should go ahead and get started. It doesn't like anybody's going to get here anytime soon, but they can go ahead and check in. No big deal. We are starting chapter 20 today, but again, I want to go ahead and give you a chance to ask me questions you might have on previous material, homework, tests or questions about the syllabus or about how things are going, that sort of thing, we do have a test that was supposed to be due tomorrow, or excuse me, was supposed to be due, since y'all meet on Tuesdays and Thursdays. It was supposed to be due Monday night at 11:59 p.m. That's definitely not going to be the case. Uh, Actually, hold on. Yeah, I'm not going to make that the case. I'm going to make it at least due by Wednesday at 11:59 p.m. just because today we're covering chapter 20, the little bit of it that I'm actually requiring you to do. And I want y'all to have one meeting time before a test would be due so that y'all can ask me any questions. So that test that was supposed to be done by 11:59 on Monday is now going to be required to be done by 11:59 on Wednesday, at least. I might push it back further, but just plan on doing that. That being said, I'm probably going to open it today or tomorrow, so you can still do it immediately, but you might not want to. You might want to take some time. As always, those online tests, I'm going to give you probably 3 attempts. Sometimes I give more. I fairly rarely give less than 3 attempts, and I only count your highest score. Remember, they're open book, open notes, open other books, open other people's notes, open internet searches. You can use Chegg and that sort of stuff. The only thing you're really not supposed to do, and the only things that I would consider cheating, is if someone in one of my classes had taken this test and seen it and then went and made notes or made a website or anything like that and read them. That would be cheating. Okay. Ideally, the person make such a thing. Ideally, the person might make a thing, but not have it based on what they learned from the test. But if any of it looked even remotely close to what the test would be, and you had looked at it, then that would be considered cheating. So I don't have any way of really knowing whether you're doing that, but it's only going to harm you yourself if you're not taking advantage of checking your learning by taking these online tests. Remember, it's the face-to-face tests that count, basically on the order of 40% and then another 25% or something like that for a final. So these are your sort of check marks to make sure you're learning the material effectively enough so that when we take a face-to-face test, you'll be prepared for it. So let's go ahead and move on. Does anybody have any questions again? I'll ask one more time before we get started. All right. Everybody, please go ahead and chat your first and last name for the role. I think most people have done it already. Maybe everybody already has. I'm going to start off with sharing my screen where I've written some stuff down. I'll read it because I did write it in cursive, and I know a lot of people aren't learning that anymore. But I think it's worthwhile for you guys to read cursive anyways. So I think it'll help you in the long run. If you learn to write in cursive, that'd be even better because if you're actually taking notes, there's really no more efficient way other than shorthand. And I think shorthand's a little in the weeds, a little technical to learn just for classes, but it might be helpful. So anyways, let me go ahead and share my screen. Well, any old time now. My wife is clearly making something that smells delicious. So I'm going to be distracted the whole class because I'm a pig. Smells like hot dogs. I love hot dogs. I know that she'd probably be offended with me saying it smells delicious and then telling them it smells like hot dogs. She's really likes her cooking and likes cooking nice things. All right, so what I wanted to warn you about is just in general, when you're taking courses, especially in the sciences and stuff like that, if you have whole chapters devoted to certain laws or principles, then the bare minimum of getting through such a course is memorizing every one of those laws or principles that have taken like up a whole chapter or a couple sections of a textbook or something like that. So as a rehash, I want to remind you that these are the ones you're expected to know at the drop of a hat. You having finished 241 at some point in the past, and you having gone through a portion of 242 now. There's only one in there that I've mentioned that we haven't covered yet, and we'll be covering that next week. So what I want to tell you is right here it says for this chapter and for any subsequent tests or exams, you are expected to know Newton's first law of motion, Newton's second law of motion, Newton's third law of motion, Newton's universal law of gravitation, Kepler's first law of planetary motion, Kepler's second law of planetary motion, Kepler's third law of planetary motion, conservation of linear momentum, conservation of angular momentum, zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, the third law of thermodynamics, Coulomb's law of force, and every version of the second law of thermodynamics as given in chapter 20 of Giancolli's Physics for Scientists and Engineers. So as you're reading this chapter 20, you should be writing down and committing to memory each of the individual versions of the second law of thermodynamics listed in chapter 20 and the name. So that's the key part about this list is not only do you have to know Newton's three laws of motion, you have to know which one's the first law, which one's the second law, which one's the third law. Same thing with Kepler's and that sort of thing. When I say conservation of linear momentum, I mean, hey, you better tell me exactly why and under what circumstances linear momentum is conserved. And that's the same thing with conservation of angular momentum. And specifically, I said at any time you are expected to be able to identify each one from a list of actual physics laws or principles and bogus statements. So what I'm telling you is there could be a time where you get to a test question and it has, several entries of long text with some equations if necessary and stuff like that. And it'll have a list of several of these names and you will be asked, which one is Kepler's third law of planetary motion, and you go through the list of all of them and pick that off. And that list of things could actually have basic physics principles. Like in here in chapter 20, you'll see a Carnot statement, basically a Carnot theorem that isn't a principle. It's not it's not one of the versions of the second law of thermodynamics. It's just a physics principle that you learn in the book. So I could put that in the list, even though that's not one of the things I required you to know. Okay. And I could just make up one and word it really nicely so it sounds beautiful and sounds like something you get from a textbook and just write that BS in there. And then you have to, of course, notice that that's not it. So just keep that in mind. And that's, basically from here out. Obviously, we haven't covered Coulomb's law. Chapter 20 covers the third law of thermodynamics. Chapter, I think it was 17, but it might have been 18, covered the zeroth law of thermodynamics. But starting with the next test, which includes chapter 20, everything but Coulomb's law is a possibility on any test from there on out. So just keep that in mind. Coulomb's law, like I said, we'll learn it pretty soon. For chapter 20, I want to give you this very specific information because I'm doing a very curtailed version of chapter 20. Specifically, here at TCC when I got here, none of the instructors were actually doing chapter 20, mainly for good reason, because we know that in the engineering program, you're going to have engineering thermodynamics, and you're going to get a much more robust introduction to thermodynamics from that. So we might as well leave it for there. It's just I personally don't feel it's appropriate to have it completed a 2-semester or 3-semester physics course without knowing the second law of thermodynamics. So I just cover it enough so you'll at least have some familiarity with it and its various versions. So for chapter 20, I expect you to be able to so this means a list is coming up. 1, calculate the efficiency for a heat engine. So I'm going to give you a general formula for efficiency that you can use on all heat engines, and that is the efficiency of a heat engine. Calculate the Carnot efficiency. So I'm also your book will derive it, and I'll show you a quick and dirty way of deriving it. But if you deal with a Carnot engine, which is part of the Carnot cycle, there's a very specific thing you can work out about the efficiency that goes from the general formula that I told you I'd give you to a more specific formula that happens to be what we call the Carnot efficiency. And then the Carnot theorem basically states that no engine can do any better than the Carnot engine. And the Carnot engine, of course, is not ever going to be even 100% efficient. So that's sort of a big deal. You're also supposed to be able to calculate notice I wrote COP, that's supposed to be the coefficient of performance for refrigerators, ACs, air conditioners, in other words, and heat pumps. So that's basically the stuff that's most critical from this chapter is being able to do stuff like the very examples I'm getting ready to work for you guys. So anybody have any questions about that? All right, so let's get started on chapter 20. And chapter 20 is the second law of thermodynamics. Specifically called, I think that's actually its name. Oh, my help. Yes, it's called the second law of thermodynamics. Okay, so that's what it's about. And what I'm going to start off with is not one of the statements of the second law of thermodynamics. What I'm going to tell you is that the efficiency in general can be defined as this. So what I'm going to say is E, that's the symbol we're using, and I don't know why it turned out so ugly when I wrote it, but E is equal to efficiency, and it is what you get, and I'll put in parentheses that's useful. So I'll just say useful divided by what you pay, or what you pay for. And in this case, I'll say total. So basically, what's going to come out when you make a heat engine is a certain amount of work that's useful. Okay. Also coming out of it is wasted heat, and that's not useful. So that's what I mean by saying all the useful stuff. What's going to come in is heat as well, and that's going to be called Q sub H, which means heat from the hot reservoir. And the exhaust heat, the stuff that's going to be wasted, is going to be called Q sub L for heat, not lost, but heat from the low temperature area. Okay. And then since QH is what's coming in, that's what you're paying. That's all the energy that came in. Even though some of it's going to be wasted, that's what you got to pay for it. Okay. And then the work is all that's actually useful. So that's what we're talking about here with the efficiency. So for a heat engine, that's normally going to be just work divided by uh, Q sub H. But if you look at a heat engine, basically what you'll see, and you'll see diagrams of this in a second, you'll find out that what the work is the heat that you put in from the high temperature reservoir minus the heat that you exhaust to the low temperature reservoir divided by Q sub H. Whoa, I just wrote that as a theta for some reason. Divided by Q sub H, which you can see reduces to 1 minus Q low over Q high. I run out of room, so I'm not going to write it that way, but you can see what it is. Actually, I'll write it up here in red. And if I write it in red, it'll stand out enough. So that's the actual ultimate formula. I find that when I'm with problems, depending on the wording of the problems and the actual problems I'm solving and stuff like that, sometimes I go straight to the W over QH and use that. But most of the time, I really do use 1 minus QL over QH. Okay, so that's something important to keep in mind. And I just wanted to get you started on that. So now what I'm going to do is go ahead into chapter 20 and talk to you specifically about the second law of thermodynamics, thermodynamics in general, and stuff like that. So let me stop sharing my screen for just a second so I can gesticulate, talk like that. I can't do that as well because my left leg doesn't, I mean, my left leg, my left arm, shoulder doesn't work very well, so I can't lift my arm. But anyways, the big deal is we have a first law of thermodynamics, which you can paraphrase to basically say conservation of energy. And that's really what the first law of thermodynamics is. And you saw, for instance, when we covered it, it was not only delta E internal is equal to Q minus W with our sign convention that we use here in physics. It could also be delta U, the potential energy, plus delta K, the kinetic energy, plus delta E internal is equal to Q minus W. And that's the more formal and complete version of conservation of energy. When we introduce relativity, we're going to discover that there's no longer a principle of conservation of mass, and I haven't even listed that as one of the things that I put on that list, for instance, nor is there any longer really a conservation of energy. With relativity, there's something called conservation of mass energy, because with the equation E equals mc squared, uh, not only can we, but we must, in every case, realize that every bit of energy comes from some change in mass. Okay. So you now can't just keep an eye on the mass or keep an eye on the energy. You have to keep an eye on both of them, because every time you have energy, in some sense created, it comes from a loss of mass somewhere. So that is the more general version of the conservation of energy. And we no longer say just conservation of mass is one thing and conservation of energy is another thing. We do have another conservation law that is a little more absolute, and that's conservation of charge. We've never found a violation of that either. I didn't mention that because it's really not that big a deal. You just, in stating it, it doesn't have any specific terminology or anything that would be necessarily helpful or conducive to your learning. You'll just learn it as we go, and it'll make sense when you go to do reactions or anything like that. So what we have here is that this first law of thermodynamics, and it's weird because it turns out there's a lot of things that still in principle can happen without violating the first law of thermodynamics, i.e. conservation of energy, but it never happens. So for instance, one thing that could happen is I could take let's say a hot piece of iron and stick it up against the ice cube. Okay. And I can just let that ice cube and hunk of iron sit next to each other. And what's going to happen is heat's going to flow from that hunk of iron into the ice cube, and the ice cube's going to raise its temperature. Maybe the ice cube was at like negative 20 degrees Celsius initially and was, of course, frozen. So what's going to happen is heat's going to flow out of that ice cube, or excuse me, out of that hot iron and into the ice cube, bringing its temperature up. And eventually it could also at least melt part of it, right? Well, that happens. We know that that happens, no problem. We even not seeing it, we still know that it would happen. But here's the weird thing. We could, in principle, take a chunk of ice and a bunch of water that used to be ice that's now melted and become actual liquid water, and might even have a temperature slightly different from 0 degrees Celsius. And we could slap that up against a lukewarm hunk of steel. And you could, in principle, imagine the molecules sort of being omniscient or knowledgeable or capable or having some kind of agency, so that they could actually just decide to do this. And you could actually pull kinetic energy away from the actual molecules of water in the ice slash water mixture. And in so doing, that would actually cool down the ice from 0 degrees Celsius, and the mixture of water and whatever temperature it is. It would actually cool that ice and that water down and freeze it while warming up the actual chunk of iron. None of that would violate the first law of thermodynamics, but we know it doesn't happen. Okay. Another one, which you've probably seen videos of before, is something like a coffee mug or a hot tea glass sitting on a table. You could, in principle, imagine it getting knocked over. It would then fall down and hit the ground and shatter, and the tea would splash all over the place. In principle, without violating the first law of thermodynamics, which is again conservation of energy, you can see the water molecules, or the tea molecules, should say, jumping out off the floor, coming together up in the air in roughly where the shards of glass are going to reassemble themselves into the shape of a tea or coffee cup. And then that tea or coffee cup could take that energy that it has, that's due to it slightly being warmer from the fall and all that good stuff, and use that energy to project itself back up onto the table. That doesn't violate the first law of thermodynamics, but we never see that happen. In fact, we're so cocky that if we saw a video of that, we'd say, oh, they ran the video backwards. Okay. So that turns out to be the essence of the first, or excuse me, the second law of thermodynamics, is it tells us what things are probable and what things can happen, and also, of course, what things can't happen. Okay. So that's what we need. Now, it turns out we first started studying this uh, when we were making heat engines. Like I told you, for instance, we use the weird sign problem with the first law of thermodynamics that's very different from chemistry. Specifically, we say the change in internal energy is equal to the heat added minus the work done by the system. That's because we were developing these thermodynamic principles thinking about the system being some kind of heat engine, and we really were curious how much work the heat engine was putting out. So that was the thing we focused on, as opposed to the energy coming in and energizing the system, which is what the chemists were thinking about, which is why they said Q plus W and we said Q minus W. Okay. So all that came to be. And of course, what we're going to get is the very first statement that your book gives on the first law of thermodynamics, or excuse me, the second law of thermodynamics. I don't know how many times I'm going to say first law when I mean second law, but anyways, your book opens up in the very beginning chapter, or the very beginning of chapter 20. I think this is, I can't even remember the page number, but it doesn't matter too much. This is an ebook. The second law of thermodynamics, and this version is called the Clausius statement, due to R.J.E. Clausius, who lived from 1822 to 1888. So you see the time frame is about the same as when people were developing Maxwell's equations and that sort of stuff. But his name was R.J.E. In other words, his initials were R.J.E. Clausius. And the second law of thermodynamics, according to Clausius' statement, is heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. So what I'm expecting you to do in this chapter is every time they mention a version of the second law of thermodynamics, I want you to write that down verbatim along with its name. And I don't need you necessarily to memorize it so that you could recite it. That's asking a little more than is really necessary. What I'm asking you to do with that is be familiar with it enough that you can identify it out of a list, as I explained to you earlier. So that was the first statement. And I tried to go through the book, and I actually highlighted like that, for instance, and all the other versions so that you one, I highlighted it and then I told it to share. And that's supposed to make all the highlights that I put available for you, my students, to see it. But what I've noticed is it's not necessarily showing up. So if you look in your book, you might not find the Clausius statement to be highlighted. In my book, it looks like it missed the second law of thermodynamics title and didn't start highlighting in the way that you can see it until after the left parenthesis where it says Clausius statement, close parenthesis, and then the statement, which is heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. So, let me know when you do look at your book, is that exactly what you see? Later, in two paragraphs below that, also highlighted a heat engine is any device that changes thermal energy into mechanical work, such as a steam engine or an automobile engine. Okay. Your footnote, by the way, says by spontaneously, we mean by itself without an input of work or some sort of uh, work being done. So basically, when we're saying spontaneously, that means it's going to be done on its own and doesn't have to have another entity supplying work or anything like that. So everybody hopefully got that second law of thermodynamics, that first version here. Then we have to turn my phone off or my watch ringer off. Stop it, run it. Okay, I can do this. There, I did it. Okay. I'd already turned my phone off, but I was confused because my watch was doing it. So we're finished with section 21. Section 20-2 talks about heat engines. And let me give you that diagram that I promised you regarding a heat engine. So now that I've discussed that a little bit, what I'm going to tell you is a heat engine is something where we have what we consider a heat reservoir. So heat reservoirs, if you remember what we talked about in chapter 18, I think it was, or 19, a heat reservoir could be pictured as like a lake. Okay, so you could do experiments on the lake, like literally sit up, a little floating table and do your experiments on the lake. And if you had experiments that were thermodynamics related, you could say, okay, well, I'm going to use this lake to cool off my utensils when I'm doing these reactions and stuff like that. And what's going to happen is at any time you can dump any amount of heat you want to directly into the lake, and the lake's temperature is not going to change because the lake is so ginormous. That's what a heat reservoir is. It's something you imagine it's immune from changing temperature no matter how much heat you take from it or how much heat you put into it. So that's what a reservoir is. With a heat engine, we're imagining a high temperature reservoir from which heat can be extracted. So this high temperature reservoir is going to cause a difference in temperature because it's a high temperature, and it's going to cause that heat from that high temperature reservoir to enter into the heat engine, whatever the heck that turns out to be. That heat engine is going to take as much of that as it can and convert it to work, and that work could be stuff that does like kinetic energy or makes potential energy. We remember it as work equals the integral of F dot dl. Now, one of the versions of the second law of thermodynamics says that you can't take all of that. Okay. If QH comes in, you're not going to get QH turned into W. You're going to get something smaller than QH turned into W. And whatever's left is going to be called Q sub L. And that's going to be the heat that's released into another reservoir. In this case, it's a low temperature reservoir, and you're going to dump that exhaust heat into that low temperature reservoir. And because it's a reservoir, it's not going to change as a result of that low heat. So in your car, you can imagine the high temperature reservoir, say, as the exploding gas that you pour into the piston, or that you put into the piston from your fuel pump and electronic emission, or excuse me, uh, your carburetor would be the easiest thing, but there's also, of course, things that we use instead of carburetors now, and I've just lost the name of that, but electronic fuel injector, that's what it's going for. So that fuel injector or carburetor sort of sneezes that mixture of oxygen and gasoline into the piston, and then the piston closes on it, attempts to crush it or to condense it, or basically contract it quite a bit. And at the instant that that piston gets to the peak of its motion, where the volume inside the cylinder is the smallest, there's supposed to be an explosion caused by a spark running across the spark plug. If it's a diesel engine, you won't have the spark plug, but the same thing happens. It's just with a diesel engine, the compression is such a large ratio that it explodes on its own. But that hot temperature reservoir is sort of what you're thinking of, because guess what? Once you've ran the engine for a good minute or so, the engine block is going to be a very high temperature, and it's going to stay that temperature, and it's not going to appreciably get hotter or colder, more or less, no matter how long you run it. So that is a high temperature reservoir. And then the gas, after it's been exploded and caused that force stroke, which is actually pushing, meaning giving the force that can turn the shaft, and that shaft is going to cause rotation that goes into your transmission, and then the transmission can re-gear that and send that out through your drive shaft or into your axle directly, for instance, if it's a front wheel drive. But either way, when it hits that, it's got to go through the differential, where it can actually encounter more gears to change ratios, especially in the rear end of a vehicle, and so on and so forth. After that force stroke is there, then another stroke will come by and compress the gas again, only this time when it's compressing the gas, it's spitting out the burnt gas out of the output. And that goes out the tailpipe into the atmosphere, and our atmosphere doesn't change appreciably because your tailpipe's putting out hot air. Okay. So that's sort of the picture of what an internal, or of what a heat engine is. So now I'm going to give you an actual drawing for it that we'll reuse repeatedly, and it's super helpful in trying to make sense of a heat engine. So let me go ahead and show that to you. It should pop up any minute now. Okay, so here's what we're going to imagine. We're going to imagine a heat reservoir. And since this is the hot one, I'm choosing to call it a temperature TH. And I'm going to do it in red so it looks like it's kind of hot. And this will be called the high temperature reservoir. Okay. Now, what you're going to imagine is a little pipe coming down from it and going into what we call the heat engine. So the heat engine is going to be this little device right here, say. And what we're going to imagine is a heat QH that's being put into the engine from the high temperature reservoir. This engine has the ability to turn some fraction of that into work. And what you're going to see is this engine puts out work in that direction. So notice the arrows are showing things. And in these quantities, this is a weird time where we're always going to use QH, QL, and W as always positive. So this is a little bit of an anomaly from the sign conventions we've been using. Now, this is not enough. In fact, you'll see later that one of the versions of the second law of thermodynamics says that this, as it's drawn right now, is actually impossible. Now that I've drawn this cold temperature reservoir, okay, what I'm going to say is a amount of heat, Q sub L, is now evacuated from the engine and put into this low temperature reservoir. So and this is the low temperature reservoir. Okay, so that's what a typical heat engine looks like. If we didn't have this little leg right here going into this, it would not be allowed. Like I said, we're going to see that later. That's one of the versions of the second law of thermodynamics, and it's just not allowed. Another way of thinking about the second law of thermodynamics is that there are sort of like two classes of heat. There's or two classes of energy, I should say. One of them is heat, and the other one is mechanical energy. And heat is a bastardized version of energy because you cannot extract all of it and turn it into work. Whereas mechanical energy, you can do 100% kinetic energy converted to 100% potential energy, no problem. But you can't do that with heat. Whenever you're trying to take heat and use and make it useful, some fraction of it's going to be wasted. So that's another version of the second law of thermodynamics. Not one I'm requiring you to memorize, by the way. It's just the ones that I listed that's listed in the book. So this is what a heat engine diagram looks like. Anybody have any questions on that? Now, for it to be useful, the heat engine has to be a cyclic thing. So it's got to go from some initial state, do some stuff, and end up back at that initial state so that it can continuously run over and over and over again. We're going to see that in action in a little bit, and I'm going to, for instance, explain to you the workings of the Carnot engine. Your book takes time to show you a reciprocating type of steam engine as well as a turbine type steam engine. And they even go as far as letting you know that in reality, virtually all power plants that we use on planet Earth, virtually all of them, at least the big ones, are run by steam turbines. So whether you're using coal, which of course produces coal is a fossil fuel, so it does produce carbon dioxide and carbon monoxide and all that stuff. But the main thing is it produces carbon and CO2, which is a greenhouse gas, and that actually contributes to what we've called global warming. So that's a little bit of an issue in that. But you could also use propane or gasoline or any other kind of fossil fuel that you want to. You could also use nuclear power. You could actually use uranium that could cook and make basically high amounts of heat. That heat could be used to heat up the steam, and then the steam would either go through a piston like it does in the reciprocating type, but more likely, since I said most of them are this type, it's going to go through a steam turbine. So basically what's happening is steam runs through a fan blade and causes the fan blade to turn. And in turning, that creates an actual mechanical work that can be used to do stuff. Like if it's turning, all you really have to do is have some magnets on it that rotate with the axle of the fan, and put those magnets turning inside of a coil of many loops of wire, and boom, out comes AC electricity. Okay, so it's really as straightforward as that. So your book talks about that. It talks about electric cars, how they can be designed. It also tells you, for instance, that a electric car doesn't necessarily have to have a transmission, for instance. So it doesn't have to like shift gears and stuff, and it can take off immediately and therefore take off really fast. You probably heard about the Tesla Plaid completing what was it, a quarter mile, or I can't remember if it's a quarter mile or if it's 0 to 60 in 1.8 seconds, but either way, it's just friggin' fast. And now I think the new Cybertruck, either the Cybertruck or the new Mack truck, can even do faster than that, even towing stuff. So it's pretty amazing. Anyways, your book also takes the time to show you a four-stroke internal combustion engine in figure 20-4. So I highly recommend you read that. So you'll have some understanding of the basics of the internal combustion engine, which is what we're currently using. Now, hopefully 20 years from now, we're maybe not using those except for in extremely rare instances, and we're using mostly hydrogen-powered vehicles or electric vehicles produced whose electricity is produced by sun or wind or tides or geothermal or something like that. But either way, I'm not going to talk too terribly much about global warming. I usually do a long section on that in my astronomy because they expect you to get that there. I will gladly talk to you about it if you want to. It is a bit of a political issue, but I tell you, it really shouldn't be. The science is solid. Uh, it's factual to say that in excess of probably 98% of all the people that are of the specialty areas of science that matter in determining climate for the globe over tens of years and decades and stuff of that case, and even centuries, probably well over 98% of the credible, relevant scientists definitely believe, one, the globe is warming. Two, it's mostly a result of man-made issues. In other words, it's mostly a result of post-industrial revolution, steam engine CO2 buildup. I have a lot of data that explains that. Some data that I've only heard, for instance, on NPR, and I've also heard it on Skeptic's Guide to the Universe, and I've of course learned it from reading actual science articles. Some of this evidence I consider slam dunk 100% proof. So if you want to talk about that, you can. I will tell you, if you really want to hear someone who knows what they're talking about, who's an expert in the field of climatology, yet doesn't completely believe in global warming and the steps we're trying to take for global warming, that person that I'd recommend you listening to is a woman by the name of Judith Curry. Curry. I think she's emeritus faculty from Georgia Tech. She's written textbooks on thermodynamics and things of that sort. She's really bright. She has some very specific arguments. Sometimes I'm not very happy with the arguments she's making, but most of the arguments she's making seem to be in good faith. Okay. Michael Mann, who's on the other side, I think he's the one that's responsible, or at least most people consider him responsible for the hockey stick graph. You can find him on Twitter or X as well. That's what I recommend you listening to them on. So follow Judith Curry on Twitter, follow Michael E. Mann on Twitter. I would tell you to go to my Twitter account and look up mine, but I don't want any of my students knowing any of my social media stuff until they finish my classes, because I don't want to indoctrinate anyone. I'll tell you, I do not consider this particular aspect of science indoctrinating just because it's such a slam dunk. I will give you access to something where you can hear some very specific Republicans say exactly that it's not a hoax, and it is something they need to get on the right side of. So I can offer that. All right. Now, again, this talks about an internal combustion engine, and then it goes into a four-stroke internal combustion engine, like a car engine. So you see exactly what the four strokes are, exactly where the power comes from. I will tell you, one of my students told me he had some friends that used to brag about their Cummins six-stroke. I had never heard of any engine being called a six-stroke, but literally Monday, I saw something pop up on Facebook where it was advertising Porsche just submitted a design for their car that's a six-stroke engine, and that's supposed to be more efficient than four-stroke. But then when my student asked me about that, I looked it up, and it turns out there are a lot of designs we've been working with for years that are six-stroke engines. I don't know if really Cummins makes a six-stroke. I wasn't able to find that, but I did find a lot of other engines. So I will tell you, by the way, the engine that's closest to what we're using far as diesels and gas engines that we use, internal combustion engines, are the Otto cycle, OTTO, which your book does a whole section on. I'm not going to require you to do that section, but I definitely recommend you read the whole chapter. But it's Otto, OTTO. And as you can guess, that seems to me like the likely culprit of why we started calling the automobile the automobile. There's also another engine that I've seen in theoretical books called the Stirling engine. And lo and behold, I do know that, for instance, Dodge makes some of their higher end trucks, some of their, 3500s and 2500s and 4500s and things like that. They make them with a Stirling engine. So I know that that's trickled down into the regular building of engines. There's a whole market in it. I mean, there's still science going on, discovering new ways to make the engine more efficient and stuff like that. But those two, the Otto and the Stirling engine, are most like the engines that we use nowadays. Now, what I'm going to show you, of course, is the actual Carnot engine. Your book does take a moment to tell you why the change in temperature is needed, why a difference in temperature is needed. I definitely recommend you read that. That's to help you understand the concepts. But then it goes into section 20-2-3, which is the efficiency and the second law. So they're going to work out. They start off, in fact, giving exactly the same formulas that I did for efficiency. So just to remind you, efficiency in general, E is equal to the work divided by Q sub H. Remember, it's what you get divided by what you completely pay for. Now, if you notice from the engine diagram, the heat engine diagram that I drew, all the energy that's going into the engine is just QH. So by necessity, that means QH has to equal work plus Q low. So from that, you can solve for work, and you'll see exactly why I got the other version. If I solve for work, I get QH minus QL. And then, of course, that's all divided by QH. And then, of course, I can break that up into QH over QH minus QL over QH, which gives me 1 minus QL over, that's a really terrible looking Q, and I'm too OCD to let it go. So that's going to be a QL, not much better, over a QH. The main thing you see here is unless the QL is 0, you're not going to get 100% efficient. You could maybe come close by letting QH be infinitely large, but where you're going to get an infinite amount of energy, you're not. So, and the QL can't be 0, as I've hinted to you. The second law of thermodynamics, one version of it tells us that QL cannot be 0. So that's the equation for the efficiency. Let me do an example, and this is example 20-1. So let's get started with that. This is 20-1, and it says an automobile engine has an efficiency of 20%. Efficient. And produces 23 kilojoules every second. Okay. Now it says like that every second. So you could actually interpret that as 23 kilowatts because a joule per second is a watt. But I'm going to stick with treating it as a joule. And what we're going to think of is the energy put out, not the power, which is what watts is, the energy put out per cycle. So when they say per second, that's another way of saying, well, you can relate the time to the RPMs of the heat engine, and then you can make some sense of what they're talking about as a per cycle sort of scenario. So I'm just calling it that. And what we want to know on this is we want to know how much heat input is required. So how much heat must be input. That's part A. And part B is how much heat is discharged as waste. So I'll just say how much heat is wasted. Whoa. I didn't mean to do that. I almost spelled waste like the waste of your pants. And now it feels like the word's not right with WASTED. But anyways, I'm going to go with it. I hate spelling. Okay. So that's the actual problem we're working with here. And this part of the course, thermodynamics, is like when you first started learning kinematics in the 241 course. Remember, you had that Greek letter nu that looks like a V, but it was clearly not a V. Maybe we didn't stress it, or maybe the professor you had didn't stress it. But the main thing is it wasn't necessarily a V, but you did know it stood for velocity. And it took a little time for you to figure out, okay, well, velocity is something that has units of like distance per time. So things like miles per hour, kilometers per second, meters per second, all of those are velocities, and therefore they get the symbol V. And then it took a little time for you to figure out that acceleration is normally given the letter A, and that normally has units like meters per second every second or something like that. Same thing's happening here. We have to be able to identify the numbers they gave us. So can anybody tell me what they think, for starters, what symbol should be applied to the 20%? So I'm going to say solution. Anybody feel free to offer me some solutions? Okay, I'm going to write here solution. Whoa, no. So what I have is the efficiency is equal to 1 minus QL over QH. That's the version I'm going to use. I do know that something we've been given is 20%, which I'm going to write as 0.20 because you never work with the percent as a percent. You almost always work on it with a decimal. So does anybody know what that percent should correspond to? Any symbols that you've seen? Okay, I'm gonna put the chat up because it looks like maybe someone's typing it in there. Yes, very good, Tanika. Excellent. So that's going to be our efficiency E. What about the 23 kilojoules? A auto engine is 20% efficient and produces 23 kilojoules of work, I should say, every second. So anybody want to give a symbol to that 23 kilojoules? The part where I said of work, that should help you. So that's going to be the actual W, and that's going to be 23 kilojoules. Okay. In part A, they are specifically asking for how much heat must be input. Does anybody think, can anybody think of a symbol that we would use for the heat input? W is right, Tanika. Good job on that one. What about this heat input? What symbol do we use for that?
Is that the QH?
That's what it is, yes. So QH is what they're asking us for in part A, And then part B, it says how much heat is wasted. Anybody want to take a poke at that symbol?
QL.
Yeah. That's it. I mean, that's basically what you have to get through when dealing with heat engines and stuff like that is just more nomenclature, more terminology and symbols and units and things like that. These are all units of energy, so they should be like in joules, but they might be in calories, they might be in BTU, stuff like that. Okay. So now I can go ahead and solve the problem. I'm going to first start off with the fact that QH is actually equal to uh, the work plus QL, right? So what I'd really like to know is what is QH. We also know that E is work divided by QH. So that version of the efficiency equation is the most helpful one. I wrote down this other one, but that's not as helpful as you can see because I have work, not QH and QL. So with that, I'm going to set and put, and I'm also going to do it like most of my students do. I'm going to put the numbers in and then solve for the symbol instead of solving for the symbols in the equation in symbolic form and then putting the numbers in, just to make it more real, like what y'all are used to doing, because I know most students do it this way. So I'm going to say 0.20. I'll put an extra zero there just to show the extra sig fig. That's the efficiency, and that's going to be equal to the work, which is 23 kilojoules, over Q sub H, which is what you pay for. So what you can see is I can say Q sub H is equal to 23 kilojoules divided by 0.200 with one extra sig fig like that. So when I do that, I can realize, for instance, trying to avoid using my calculator, 2.2 is 2 over 10. So basically what we're going to do is take and multiply that 23 by 10, that make 230, and then we're going to divide it by 2, so that make it 115. So I'm going to say QH is 115 kilojoules, and technically we don't have that many sig figs, so I technically have to put a underbar under that 5, but that's sufficient for the answer for part A. Anybody have any questions on that? That makes pretty good sense, right? All right, now the next part they're asking for part B, they want to know what QL is. And notice I did write that QH is equal to L plus QW. So now we can see for part B, oops, we can see for part B, QH is equal to W plus QL. So all we need to do is say that QL is actually equal to QH minus W. So I'm going to take the 115 kilojoules and I'm going to subtract from it 23 kilojoules. Now I know 100 minus 23 kilojoules would be 77, and then I need to add another 15, so that'd be 87, 92. So the result is in fact 92.0 underbar kilojoules. That's how much heat is wasted. Now that's not necessarily the only way to do it. For instance, we could have used one of the original principles. We could have used E. So I'll write this as alternative. So just in case anybody was thinking of trying it this way, I'm letting you know that this in fact works. We know E is equal to 1 minus QL over QH. So you could have written 0.20 underbar equals 1 minus QL over 115 kilojoules, because we already worked out that the QH was 115 kilojoules. That would mean that we get basically QL over 115 kilojoules is equal to 1 minus 0.20, which gives me QL over 115 kilojoules is equal to 0.80, again with an extra 0 for a non-sig fig. And now I can see that QL would actually equal 0.800 times 115 kilojoules. I know that zero point 0.8 times 100 would give me 80. And then 0.8 times 15, I could basically say that's the same thing as 1.5 times 8. That would give me 8 plus 4 would be 12. So I'm going to say this is 80 plus 12 or 92. And you see that we got the same answer again. Any questions on that one? All right, so notice, as always, there's usually more than one way to solve a physics problem. So don't assume because you did it one way and the book or me did it another way that you did it wrong. There's a good chance that you got it right. The best way of figuring it out is trying your way. And if you get the same answer I do, it's pretty unlikely that you are wrong. However, there are times when you can get the right answer for all the wrong reasons. It is kind of a bummer when you find it, but just know that that is a possibility. So you always want to keep that in mind. All right, now that I've talked about efficiency in the most general terms, now I'm going to tell you exactly what a Carnot engine is. So a Carnot engine was imagined by a man by the name of Sadi, S-A-D-I Carnot, who was a French scientist. He lived from 1796 to 1832, according to your book, and he was studying the characteristics of an ideal engine. So he's actually looking for a heat engine, and he tried to imagine an ideal one, and then he'd work as if whatever efficiency that ideal engine had, that would be sort of the goal that you're shooting for with a regular engine. And what he came up with was the Carnot engine. And the Carnot engine is basically an engine that's impossible to make. It's reversible for starters. So what we mean by that is uh, each step in the process of the engine. Remember, it's some sort of cyclic thing that starts at one point, does a bunch of stuff, and then returns back to that same point. But each little move from that very first point to the next point, and then from that next point to the next point, each one of those is only infinitesimally small from an equilibrium point. So you're going from one equilibrium point to the next, and all it takes is just a slight tap and it will go back to the state that it just came from in a non-destructive sort of way. In other words, in a conservative way. Because remember, generally speaking, things like friction would actually make that not possible. So once you went, ahead by a millimeter, you had a millimeter worth of friction that did a millimeter worth of friction work on it, and then you lost that much energy. So if you went back, you'd end up losing even more, and there's no way you'd get back to the original state. So by imagining this engine as a reversible engine and quasi-static, which is why it's a string of equilibrium points, we've basically introduced a perfect engine that has no friction and that goes really, really slowly and is reversible at every point. Okay, so that's the fundamental idea behind Carnot. And remember, as you're reading this chapter, like you do in all chapters of our book, anything that's italics or anything that's bold print, you want to just assume that you're going to have to know that and go ahead and commit it to memory. So now let me draw a diagram. This will be a PV diagram for a Carnot engine so you can have some sense of exactly what the Carnot engine is and how it works. So I'm going to draw a vertical axis for the pressure, and I'm going to draw a horizontal axis for the volume, like so. And what I'm going to imagine is that there are two isotherms. Remember, isotherms are lines in a PV diagram, for instance, that represent a fixed temperature. So I'm going to imagine one fixed temperature like that. And that's going to correspond to a temperature TH, which happens to be the temperature of the heat reservoir I talked about earlier. And now I'm going to imagine another isotherm whose temperature is TL. Okay. Now what I'm going to imagine is starting at point A, in other words, at a particular pressure and volume, is a location we're going to call A, and I'm going to imagine obeying or following that isothermal line from A down to a point I'm calling B. So this point right here is going to be B, and I'll put the arrow on it to show you that we went from A to B along an isotherm. During that process, however, there was a certain amount of heat, QH, added to the Carnot engine. Okay. Now you can see that we're going from low volume to high volume. I mean, from low volume to lower volume still. Mm, No, we're going. I'm sorry. All this time I've been thinking for some reason that we're going from low volume to high volume. I don't even know why I considered that. But basically, from A to B, we're going through an expansion. So notice the volume went from a low quantity under A to a high quantity under B. And now all of a sudden, there's going to be an adiabatic uh, change. This time it's also going to be an expansion. So now I've got an adiabatic expansion. Oops, I didn't mean to do that in black. An adiabatic expansion, which has a special line itself, but the line is very much different in equation form than the isotherm. And this part right here, I'm just going to say is an adiabatic expansion. Again, this is an adiabatic expansion, which means one, that the volume's getting larger, but two, the adiabatic part means that no heat is being added during that expansion. Okay, so that's an adiabatic expansion. Notice we're still going from left to right, so it's still an expansion. This right here is an isothermal expansion. Oops. Now, after the adiabatic expansion, then we're going to do another isothermal uh, process, only this time it's going to be an isothermal compression. So this will be point D here, and we're going this way, and it's isothermal, not adiabatic. So in this part, we can actually have the heat Q sub L put out. Okay. And then from there, we got to go back to our initial state. And to do that, I'm just going to go right along another adiabatic compression. So this part's going to be another adiabatic process, and it's an adiabatic compression. Whoa, Nelly. So that's basically the Carnot cycle. Okay. So you're seeing basically, you can imagine a gas and a piston. Okay. So by a gas in a cylinder. So you imagine like a cylindrical shaped container, maybe made out of a very thick aluminum or steel or something like that. And then you have a piston down at the bottom that allows you to shrink the volume of that cylinder by moving up, making it a smaller volume, which is compression, or moving down to make it a larger volume. So in A to B, what's happening is that gas, or the working substance is what your book is calling it. That working substance is actually being expanded by something. We don't really know what it is, but what we do know is heat is coming into it. So it could be one of those things that heat came in and caused it to actually expand on its own. That expansion, which is basically pushing a piston upward or downward, depending on your orientation, but that could in principle do some kind of work or something, right? So heat coming in, we imagine cause the isothermal expansion, and it's isothermal because heat takes a while to go from one substance to another. So for instance, when you actually put in the QH, that actually causes the gas to expand, but it's going to take some time before the gas could actually change temperature, because what has to happen is the average molecular velocity, translational velocity of the molecules in the working substance has to get larger, but that's the average, not a particular one. So you can imagine that as isothermal, because it's going to take a little while for the temperature to actually rise. So basically, no temperature was rising during that expansion, but then the temperature did finally, in this case, cool down because it expanded. So when it cools down, you expect it, when you expand it, you expect it to cool down. When you compress it, you expect it to heat up. So the heat coming in made it expand. And then as it expanded, it cooled off from temperature T high to T low. That process can basically made it expand just a little bit further. And in so doing, that was an adiabatic process where no heat could be allowed in. At that point, the piston then began to compress the gas and spit out a heat Q sub L. And after that, the process was followed, for instance, with a adiabatic compression further to A, and we're completed with the cycle. So what we're going to do now is, starting from that same formula, E equals 1 minus QL over QH. Your book is going to use the ideal gas law, as well as that P1 V1 to the gamma power is equal to P2 V2 to the gamma power. It's also going to use work equals the integral of PDV and all that good stuff, and the PV equals nRT. All that stuff is going to be used to conclusively and correctly derive a formula for the Carnot efficiency. Okay. I'm going to do a different trick, and I'm going to introduce what's called entropy. And entropy is defined such that the change in entropy is equal to the heat added to the system divided by the temperature at which the heat was added. If the temperature is changing, you're going to have to break it up into little segments and stuff like that. But that's called the entropy. And what we find out is entropy always increases except during reversible processes. And that means delta S equals 0 for reversible processes. Okay. So we've already made the argument that Carnot was imagining a reversible heat engine. So from that, we know delta S is going to be 0. So delta S equals 0 gives us that QH, which came out at temperature TH, is equal to QL, which came out at temperature TL. And that means that QL over QH is actually equal to TL over TH. So now we have the Carnot efficiency is equal to 1 minus T low over T high, like that. And again, you see that the efficiency cannot be 100% unless TL is 0. Okay. That's actually another law called the third law of thermodynamics. It says there's no finite number of processes that can be done to bring anything to 0 Kelvin. And all these temperatures, by the way, have to be in Kelvin, because we're all coming from the ideal gas law. So just keep that in mind. But now we have the Carnot efficiency, and I skipped it by doing this nice little trick about the entropy. Okay. I highly recommend you reading the derivation and understanding it, and maybe even ultimately trying to figure out if you can come up with it on your own at some point. If you can, then that's great. If you can't, then wait. Maybe you'll be able to do it after you take your thermo class. So now we have the Carnot efficiency, which is also called E ideal. I noticed your book wrote that, so I'll write that too. E ideal. Okay. So here's the Carnot theorem. Remember, this is the one I warned you about. This is a Carnot theorem. It's not a second law of thermodynamics. It's not one that I'm requiring you to be able to identify. That being said, it's still important, so I'm going to read it to you. According to the theorem stated by Carnot, all reversible engines operating between the same two constant temperatures, TH and TL, have the same efficiency. Any irreversible engine operating between the same two fixed temperatures will have an efficiency less than this. So what that means is engine efficiency, heat engine efficiency is always going to be less than the Carnot efficiency. And if you find another ideal reversible engine like the Otto cycle or the Stirling cycle or any of these other ones that have come up, if they are truly reversible and they're operating between the same two temperatures as the Carnot engine is, then they'll have the same efficiency, and an actual engine would have less efficiency than that. Okay, so that's the Carnot's theorem. So let's look at example 20-2. So this is example 20-2. It says a steam engine operates between 500 degrees Celsius and 270 degrees Celsius. What is its maximum possible efficiency? So, solution, max theoretical efficiency is less than E Carnot, which equals E ideal, which equals 1 minus T low over T high. Anybody want to take a guess what T low and T high are? Which of those temperatures you think is T low?
270.
Yep, it's the 270. Only we can't use 270. It's got to be in Kelvin. So I'm going to say 270 plus 273. And that's going to be called, of course, 400, 540, 543. And then T high is going to be 500. But again, we can't use Celsius. So it's going to be 500 plus 273, which is 773 Kelvin. So the Carnot efficiency would be 1 minus 543 over 773. Those units, of course, are canceling each other out. They're both Kelvin, but they cancel each other out. So you end up getting one, a pure number, minus another pure number. So what I'm going to do is I'm going to take 1 minus parenthesis 543 divided by 773, close parenthesis, and that gives me 0.2975 as the efficiency. Technically, they could have given us 2, they could have given us 3 sig figs. I'm not really sure, but I'll just put the underscore by the 5. So we know, oops. This engine will be less than 29.75% efficient. Any questions on that one? All right. We're going to do the next problem, which is example 20-3. So example 20-3, we've only got about 4 minutes left. This is okay. The rest of the examples, like I said, are coefficient of performance examples with refrigerators and ACs, and coefficient of performance with a heat pump. And you'll see how they're defined. You should be able to do just the most rudimentary plug and chug examples on that, and that's pretty much it. But anyways, I'm going to go ahead and work this out. What we have is an engine manufacturer makes the following claim. So this is their claim. Heat input equals 9.0 kilojoules at 435 Kelvin, and heat output is going to be 4 kilojoules, and that's supposed to be at 285 Kelvin. And you're supposed to answer, do you believe it? Okay. So the absolute efficiency we can still calculate, and that's really what we need to do, is calculate the efficiency and see how the efficiency compares to the Carnot efficiency. So I'm going to calculate both. So I'm going to say E Carnot is equal to 1 minus TL over T high, and I'm going to say E is also equal to 1 minus Q low over Q high. So the Carnot efficiency is actually 1 minus, now we're going to say 285 Kelvin. Notice they gave it to us in Kelvin already, divided by 435 Kelvin. And when I do that, I get 1 minus parentheses 285 divided by 435, close parentheses. That gives me 0.3448. Okay. Now let's calculate the actual efficiency. That's 1 minus QL over QH. So that's going to be 4.0 kilojoules over 9.0 kilojoules. 4/9 is, of course, 0.44444. So we're going to get the efficiency is 0.5556, which is greater than E Carnot. That's a big red flag. If you ever have an efficiency someone's claiming is higher than the Carnot efficiency, you know they're either ignorant and don't understand what's going on with the process they're working on, or they're liars. Okay, so there's no ifs, ands, or buts about that. We've never found a violation of the second law of thermodynamics, and one version of the second law of thermodynamics is that basically you cannot make anything better than a Carnot engine. Okay, so we'll see that later. So now we've finished another example. I'll say no. That's the answer. All you have to do for the rest of this chapter is I want you, and I might make some videos of these just to have you have more examples, but you can also look on my YouTube channel for other versions where I did chapter 20. So you can just look through and look for Carnot, C-A-R-N-O-T, in my YouTube channel, and you'll find a lot of problems I solved. But if you go through the chapter, you'll see, for instance, the next second law of thermodynamics, which is called the Kelvin-Planck statement, is no device is possible whose sole effect is to transform a given amount of heat completely into work. That's another version of the second law of thermodynamics, and you should know not only it, but you should know that that's the Kelvin-Planck statement. That's what I was warning you about earlier, that if you had a heat engine that didn't have a cold reservoir in which Q sub L was dumped, then that's not possible. Okay. So you got to go through the rest of this chapter, reading all these different second law of thermodynamics and writing them down so you can commit them to memory to some extent. You can see they cover section 20-3-1 is the Otto cycle. That's an extra section that you don't have to cover, but it does show you basically an isothermal process followed by an isovolumetric, followed by an isothermal. That might be an adiabatic, come think of it. I forgot about that. So it's adiabatic, then isovolumic, and then adiabatic, and then isovolumetric again. But anyways, that's the Otto cycle. I'm not going to ask you any questions about that. You don't have to do anything. But what you'll see is for refrigerators, there's something called the coefficient of performance. And for a refrigerator, that's COP equals QL over W. Because for a refrigerator, what you're imagining is you're stealing heat from a warm place, or for a refrigerator, you're taking heat from a cold place in and putting it out into a warm place. So what you get is the QL. So this is TL and this is TH up here. So what we're imagining here is we're going to get a heat QL pulled out of the cold refrigerator or the cold house, and in order to do that, we're going to have to put in a work W, and in addition to that, that excess heat is going to be pushed out into the warm reservoir, which is temperature TH at QH. So that's the efficiency of an AC and a refrigerator. So you need to know that, but then you'll also see a coefficient of performance for a heat pump. And that one is you're taking heat out of the cold environment, excuse me, taking heat out of the warm environment and dumping it into the cold environment. And what you're paying for is work. So this is for a heat pump. That's all you need to do is go through this chapter, copy the various versions of the second law of thermodynamics and their names, and then make sure you can do these two types of examples in addition to the two example types that I just did. You guys are free to go. Make sure you did put your first and last name in the chat. I hope you have a good time. Remember, you do not have a test due Sunday. I'm also not going to make this homework for chapter 20. I'm not going to make it due Sunday. I'm probably at least going to make that due Wednesday night at 11:59 p.m. So have a good one, everybody. Thanks for coming.
Thank you. Have a good weekend.
You're welcome. Thank you. Thank you, Hannah. Oh, that's it. Everybody left. Bye-bye.